Welcome to Ares Station. Today, we're deploying a planetary rover, and you are the science officers in charge. But before we touch down, we need to address the physics of talking to deep space. Look at this orbital geometry. A radio wave takes 4 to 24 minutes to cross between Earth and Mars. If a rover hits an obstacle, you're staring at up to 48 minutes of dead air before your command reaches the surface. It sits frozen. Standard AI models require constant, high-bandwidth server connections to function. Put a cloud-dependent system on Mars, and the moment it loses that umbilical cord to an Earth data center, it stops working. A rover cannot phone home to make a decision. To survive, its brain has to ride along in the chassis, operating completely cut off from the outside world. To solve this exact constraint, Meta developed Muse Glimmer. This is a 30 billion parameter open-weight AI model designed from the ground up to run offline. It executes local, always-on tasks without ever pinging an outside server. Glimmer operates as an autonomous agent. It is trained to command hardware, read sensor data, and analyze physical environments directly from the chassis. Getting a model this capable onto local hardware introduces an immediate physical problem. At full precision, 30 billion parameters require over 55 gigabytes of memory, far exceeding the limits of standard edge compute modules. To shrink the footprint, developers use a process called 4-bit quantization. This mathematical compression technique reduces the precision of the model's weights, squeezing the entire neural network down to under 20 gigabytes, while maintaining its logic and structure. By reducing the memory requirement, the AI can run entirely on a single consumer graphics card, like an RTX 4090, or a modern high-end laptop. That tighter footprint leaves crucial memory open. It gives the system enough leftover capacity to run Glimmer's visual perception encoder, allowing the AI to interpret image data at the exact same time it processes text. And to keep those responses fast, Glimmer includes a lightweight drafter model called DFlash. Instead of computing one word at a time, this companion network proposes entire blocks of 16 tokens at once for the main model to verify. These optimizations yield a system that feels live and responsive. The rover gets a highly capable real-time brain operating entirely within its offline hardware limits. So how do we physically connect this local brain to an alien landscape? We use a 3-tier hardware stack. In this architecture, the Arduino base layer tracks microsecond exact physical events. The Raspberry Pi middle layer translates this into wireless data endpoints. At the top, the laptop runs Muse Glimmer, asking for sensor readings and executing autonomous logic. By separating the system into these 3 tiers, we isolate the time-critical reflexes of the physical sensors from the complex, high-level cognitive reasoning of the AI. Let's introduce a complication and pull a wire mid-experiment. If a typical chatbot lost its sensor connection, it might attempt to fabricate a reading. On another world, hallucinating physical data gets the rover destroyed. Muse Glimmer is trained to refuse fabrication. It prioritizes failure recovery as a core operational principle. When the data stream cuts out, Glimmer reads the exact system error, realizes the rover bus is unreachable, and pauses. It explains the precise fault to the operator in plain language and prepares to retry the command once the physical link is restored. The ability to diagnose a hardware fault, report it accurately, and safely hold position is the dividing line between a novelty software demo and a machine you can actually trust 40 million miles away. Now, let's break the simulation. We aren't actually on the surface of Mars. We are sitting at a high school physics bench. The communications blackout is a design constraint for the classroom. By framing the public internet as Earth, a resource 20 light minutes out of reach, the rover is forced to solve problems with the compute it carried to the bench. Because Meta released Muse Glimmer under the OpenWeight's Apache 2.0 license, educators and builders are free to fully own, fork, and fine-tune the model for their specific curriculum without any restrictions or fees. And most importantly, because this model runs completely local on classroom hardware, no student data or private telemetry ever leaves the physical room. This specific setup teaches the mechanics of gravity, but the underlying lesson applies to the entire future of robotics and embedded systems. True autonomy dictates that an AI must be able to reason exactly where it stands. When the environment is harsh and the network is down, there is no cloud server coming to bail it out of trouble. The tools are available right now. Download the model weights, build your hardware stack, unplug the internet, and let your machines measure the real world.